Okay, today we are going to finish section 8.4, which will finish everything that we're going to learn for the semester. So this is kind of the last section that we need to cover before the final exam. If we go to our workbook, this is where we left off. To finish section 8.4, we essentially need to talk about what happens when we look at a geometric series, but we don't compute the sum of the first n terms. Instead, we're going to look at infinite series, which are represented by the three dots. If you just have like 2 plus 4 plus 6 plus 8 plus dot dot dot, and you don't include a starting point, that is representative of an infinite series. In this specific example, 2 plus 4 plus 6 plus 8, these numbers are growing because we're adding 2 every time. This is not even a geometric term. This is actually an arithmetic term, right? Because we have an increase of 2 between terms. Explicit formula would be 2 times k, where k goes from 1 to infinity. So you can identify infinite series by either the numbers or the sum written out with a dot 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 at the end, or if you have it written in sigma notation, if you have an infinity at the top, that means the numbers never stop. You plug in 1, you plug in 2, you plug in 3, and so on forever. And we want to know if this sum has some kind of meaningful numerical answer. And in this case, it doesn't, because this series is said to diverge because these numbers are getting larger and larger, and if we add infinitely many of them, we call that diverging. We can say that the sum is infinite because infinity is not like a number answer, we just say that the series diverges. But some geometric series, even though you're adding infinitely many terms, can converge to a numerical answer. And how we know that they converge is when when the common ratio of your geometric series is less than 1, or the absolute value is less than 1. Meaning, if your common ratio is between -1 and 1, then the series is said to converge, and we will have a formula for finding that sum in those instances. So remember that if you have a series written in sigma notation, this explicit formula here, you should be able to identify the first term and the common ratio raised to the k minus 1 power. So this common ratio you should be able to determine from looking at the explicit formula. If you have it written out in expanded form, kind of like these two examples here, you should be looking for a common ratio by dividing consecutive terms by each other. So first of all, we want to decide whether each sum is defined, whether it converges to a specific number or it diverges. This first example here, we see that this is not a geometric series, because we see a -4 -4 relationship, which means this is an arithmetic series. And if we keep doing -4 -4, these numbers will eventually end up in the negatives. So like the next one would be 0, the next one would be -4 and -8, and so on. And so we'll get infinitely many negative values added together. This series is going to diverge. Almost, oh, I don't want to say almost. Yeah, almost every single arithmetic series will diverge. There is one specific example of an arithmetic series that doesn't diverge, and I will let you figure out which one that is. Example 2, however, or part, let me talk about part, let me talk about part C. Part C, I don't know if it's arithmetic or geometric, so let's let's put it to the test. If I want to check if it's geometric, because if it is geometric, then we want to know what r is. To find r, we're going to want to take a term and divide by the previous term to find that common ratio. So I want to take 1/2 and divide that by 3/4. In order to divide fractions, we take the second fraction, we flip it, and we multiply. So 1/2 times 4/3, which simplifies a little bit. This becomes a 2, this becomes a 1. We get 2/3. So when we divide the second term by the first term, we get 2/3. Let's do the same thing with the next set of terms. So if I take the 1/3 and I divide that by 1/2, we flip that second fraction and we multiply. So 1/3 times 2/1, which again gives us 2/3. So this tells me that we get from one term to the next by multiplying by 2/3. So this is the common ratio r. So this is geometric. R is equal to 2/3, and therefore it converges. Because this r is less than 1, or it's specifically between -1 and 1, or if we take the absolute value, it's less than 1, we can say that this infinite series converges, which means we can actually find this sum, even though there are infinitely many terms, we can find that sum using the formula that's coming up on the next, is it the next page? Yeah, coming up on the next 2 pages away. So, but for now, we're just concerned whether it converges or diverges, meaning is there an answer we can find, or does it go to infinity or negative infinity? Right, so you guys can do the other examples there. When the sum of an infinite series exists, we can calculate the sum. The formula for the sum of an infinite series is related to the formula for the sum of the first n terms of a geometric series. So this was the formula that we've seen for the nth partial sum of a geometric series, where we know how many terms are adding up. Now, when we take this n to infinity, some interesting things happen. Essentially, if the r is between 0 and 1, so like 1/2, for example, and you take 1/2 to the nth power and you let n grow larger and larger, essentially to infinity, what happens is that this 1/2 to the n will eventually approach 0, right? If you take 1/2 to the second power, that's 1/4, which means it got smaller. If I take it to the fourth power, that's 1/16, which is even smaller. To the sixth power is 1/64, which is even smaller. 1/2 to the 10th power in this table is 1/1024. That's even smaller. And I don't even know what 1/2 to the 20th or 30th is, but they're very, very small numbers. They're 1 over very large numbers. You can fill out those by taking 2 to the 20th power and 2 to the 30th power if you want to finish filling out this table. But the point is here that these numbers are getting smaller and smaller. So we can say that these numbers approach zero. All right, so if that r to the n value is going to 0, then what happens to this formula is as n goes to infinity, r to the n power will go to 0. So a1 times 1 minus r to the n divided by 1 minus r. This thing in here, the r to the n, will go to 0. So we can replace that with a 0. So as n goes to infinity, we have that this formula will become a1 times 1 minus 0 over 1 minus r. All right, and we can simplify that a little bit. we can say, well, 1 minus 0 is 1, so we can write the numerator as just a1 over 1 minus r. So that's what happens to the formula as n goes to infinity. As long as r was between 1 and negative 1, as long as r is a fraction smaller than 1, when you go to the infinite series, that r to the n is going to turn into 0. That'll go away, so you get this formula here, which is the formula on the next page for the sum of an infinite geometric series as long as r is, or absolute value of r is less than 1. So now we're able to find the actual sums of these infinite geometric series by using this formula. So any one of these series, not any one of these series. We still have to make sure these are, we still have to make sure that they fit this criteria of being an infinite geometric series with an r that's between negative 1 and 1. So first example here, 10, 9, 8, 7 added together forever. This is a arithmetic series. This is arithmetic. Thus, it diverges. Right. First of all, it fails the first test of determining whether determine if the sum of each series below exists. This one doesn't exist because it diverges. It goes to negative infinity because these are decreasing. Second example, this formula, 9 times 1/3 to the k minus 1, looks like the formula a1 times r to the k minus 1. Therefore, the r in this geometric series is 1/3. R equals 1/3. This is geometric. And r is, absolute value of r is definitely less than 1. So we can confidently say that this one converges. And the sum, like the actual sum, if I added all of the terms of the series together, will follow the formula a1 over 1 minus r, which we can find the first term by plugging in 1 into this k. 1 plugged into here, 1 minus 1 is 0, 1/3 to the 0 power is 1, so we just get 9 for the first term. And then 1 minus r is 1 minus 1/3. So simplifying that, we get 9 over 2/3, and then we flip and multiply. 9 times 3 is 27 over 2 is what we get for that sum. So if I were to list all of the terms out and add them together, that sum would approach 27 over 2. Any questions so far? Okay, you guys can do those last couple of problems. And then finally, the question of annuity problems. We did an example like this in example 8.4.1. Which if we go back to 8.4.1, that's a while back. 8.4.1. Oh, we didn't do it, but we should probably do this. Interest compounded annually. How much money will they have saved after 1 year, 2 years, 3 years? How much money will they have saved when their daughter is ready? I think there was actually a worksheet problem like this one somewhere. I thought we did one like this. So a couple decides to start a college fund. Well, I just went back to the beginning of chapter 8.4 so we can answer this question. Decides to start a college fund for their daughter. They plan to invest $6,000 in the fund each year. So actually putting in $6,000 every year. The fund pays 6% annual interest, compounded annually. How much money will they have saved after 1 year? Well, after 1 year, they will put in 6,000. So after 1 year, they put in 6,000, and the fund pays 6% annual interest. So that gets multiplied by 1 plus 0.06. So essentially 6,000 times 1.06 to figure out how much money they have, how much the interest rate increased the money after 1 year. When we multiply that, what do we get? Times 1.06 gives us 6360. After 2 years, we would have that previous answer. So 6,000. So this is representing the first year, 1 times 1.06. Plus, they would add another 6,000 because at the beginning of the second year they add a 6,000 to the bank, and then whatever that total is would get multiplied by 1.06. Meaning, if I distribute this 1.06, I get 6,000 times 1.06 to the second power plus 6,000 times 1.06. Or if you want to think about this, the first $6,000 they put into the bank gets multiplied by 1.06 twice because that's 2 years. And then the second year 6,000 they put in gets multiplied by 1.06 once. Right? And that'll be some value. Now, if we write out the third year, we're going to see that it looks like 6,000. The first 6,000 they put in will get multiplied by 1.06 3 times. The second 6,000 they put in will get multiplied by 1.06 twice. And the most recent 6,000 they put in will get multiplied by 1.06 once. So we see some kind of geometric series forming here where we have 6,000 as the A1, and then the 1.06 is the R, right? We see 6,000 times 1.06, 6,000 times 1.06 squared, 6,000 times 1.06 cubed. So it looks like that formula, and we're adding all of these terms together. So this is essentially a infinite geometric series question written in the form of a bank with interest being paid out. How much money will they have saved when their daughter is ready to start college in 6 years? Now, we don't need to write out all of that for the 6 years. 6 years will be, we can write it in summation notation where k goes from 1 to 6. And we would have 6,000 times 1.06 to the k power. So that would be what the 6 year after 6 years looks like for the summation. And we can actually compute that because we have a formula for finding the 6-term sum of a geometric series. So we could compute that using the formula that we learned in 8.3. I think, no, 8.4. We learned in this 8.4. the sum of the first n terms of a geometric series. But now we're revisiting that problem at the very end of 8.4. So let's look at the new example. Suppose instead of investing $6,000 annually, her parents decide to invest $500 a month, which is essentially the same thing as $6,000 a year, but they're investing $500 a month in an account which pays 6% annual interest compounded monthly. So if it's compounded monthly, but it's an annual interest rate, then the monthly compounding, the monthly interest is actually 0.06, which is yearly, divided by 12, because there are 12 months. So that's the essentially the interest rate that's being compounded monthly. How much would be in the account after 6 years? Use the partial sum of geometric series. So if we adjust our formula from before, 6 years, we also need to convert to months. 6 years is equal to 6 times 12 months, which is 72 months. So we're going to have a sum that goes from 1 to 72, because there are going to be 72 instances of interest being compounded. And they're putting in $500 a month, so our starting amount is 500. Our common ratio, the interest that's being compounded monthly, is this 0.06 divided by 12 number. And that's going to be compounded every month, starting with 1. So we'll take that to the kth power. So this series will tell us the how much will be in the account after 6 years. So if we were to write some of the terms of this series, we would do 500 times 0.06 divided by 12 to the first power, 500 times 0.06 divided by 12 to the second power, and so on, all the way to 500 times 0.06 divided by 12 to the 72nd power. So we're going to have 72 terms in this sequence, or in this series. If we want to find the sum, we want to find the sum of the first 72 terms here. And our formula, if you remember, is this one that we just saw on this page here. This formula, or this formula given up here, the a1 times 1 minus r to the n divided by 1 minus r. So a1, which is the first term, is 500 times 0.06 divided by 12 times 500. Sorry, this is just going to give us the interest earned. We forgot to add the 1. Let's fix that. We forgot to add the 1 in here. This will just compute how much interest is earned. How much would be in the account would be 1 plus 0.06 divided by 12. So if your interest percent is 0.06 divided by 12, then you actually end up with 1 plus that, because you also have the 500 that you put in, plus the interest that was earned. So if we do that, we get 502.5. I don't know why I wrote it up there. Oh, I know why. 502.5 times 1 minus r, which is, if you evaluate one of these, I guess we can evaluate this one here. This one evaluates to 1.005. So 1.005 to the 72 power divided by 1 minus 1.005. And when we calculate this, what do we get? 1.00. Can we calculate this? We can. Give me a second. Uh, 502.5 times 1 minus 1.005 raised to the 72 power divided by minus 1.005. And that gives us 43,420.45 and 45 cents. So in dollar amounts, that's how much will be in the bank after 6 years. Now, remember that they are essentially putting in $6,000 per year into this account. So already that $6,000 per year times the 6 years, the parents are putting in $36,000. But because of the 6% annual interest rate compounded monthly, that $36,000 turns into 43,420.45. Right, so the interest is increasing that that amount by about 7,400 ish. Okay, I will stop there.